Good evening, sir.
Yeah, good evening. So the recording is started. Okay, let me share my screen. Okay, I hope you can see my screen, right? Okay. Let me move this one, right? So from current slide. Okay, so this is week 5, right? Let me uh, wait here. So week 5 and uh, yeah. So week 4, what we did, we discussed perceptron. So the video is available on YouTube. So if you can go there and see. Okay, so we also implemented how, let's say, the exact linear regression solution work, right? That was also that X transpose X inverse X transpose Y, that solution, and how we get gradient descent approach is basically different from it. Okay, so how let's say instead of doing an exact solution, you can follow the error curve or error value, and based on that kind of optimize your parameters like weights and biases for a perceptron model. Okay, and then we implemented two perceptron based methods. One is this linear and logistic regression using the scikit-learn library. Okay, and we implemented for two examples, car price and iris. And later on, for support vector machine, there was a video link given. So that's from one of the professors from MIT, and he did a very great job explaining how support vector machine works. So for a reference, apart from your current coursework, current course videos, you can see that video from week 4's slides. Okay. So now in week 5, what we will do, we will first discuss the doubts from week 3 and week 4. Okay, because the deadlines are over, and I have uploaded the previous runs of week 3 and week 4 in the drive folder. And what we will do, we'll learn. So for till now, you have introduced to perceptrons, right? How it works. So we'll just touch upon that in a bit. And this week we will kind of see how neural networks are formulated, and how the backward forward pass are done, and how we can use a neural network to get good accuracy on a, let's say, a handwritten digit data set. Okay, so that's the basic example everybody do for when, let's say, someone is learning neural network for the first time. What they do, they try to implement a classifier for handwritten digits. Okay, um, okay, so yeah, so that's the entire plan of today. So doubts, let's see the drive folder. Okay, previous run questions. Okay, I hope you have already given a look on this, right? That mostly, so the first one, right? So you have a two class. So let me just zoom in. Yeah. So the first two class problem. So first, for a two class problem using discriminant function lambda k, discriminant function for class k. Okay, where the separator hyperplane located. So separator hyperplane is located when where the lambda 1 is equal to lambda 2. Okay, so that means basically the middle ground of the probability function. See, and okay, so this one is easy. Given the following dataset consisting of two classes A and B, calculate the prior probability of each class, where the prior probabilities of class, okay, what are the prior probabilities of class A and B? So that means uh, only the P of A and P of B, right? So you can just compute it from this class distribution. Yeah. So just take how many A's are there divided by total number of A's. So 1, 2, 3, 4, 5. 5 divided by 1, 2, 3, 4, 5, 6, 7, 8. 5 divided by 8. That would be, yeah, 0.625. So 0.625. Option B is correct. Okay. Now, yeah. See the three-class classification problem using linear regression. The output vectors for three data
So
points
didn't
are
you
this.
calculate for B, sir?
Why? Uh, can you repeat?
So can you show the second question?
Yeah, second question, it is the prior probabilities of class A and class B, right? So you can just count the number of A's by total number of classes and count the number of B's by total number of classes. So what I did, I just count the number of A's divided by total, that becomes 0.625. So option B is correct.
Yes, I got it, sir.
Got it. Okay. So these are just counting problems, basic counting problems. Now, class 3, right? In a three-class problem using linear regression, the output vectors for three data points are this, this, and this. To which class would these points be arranged? Okay. Three-class algebra using linear regression, the output vectors for three data points are this, this, and this. To which class would these points be arranged? Right. So now this one. So I think what you have to do is a three-class problem using linear regression. The output vector for three data points are this. In which classes would these points be assigned? This is a bit confusing question. So I'm not sure what they mean by assigned. Okay, or how these 3 points be assigned. So the answer is obviously D. So 1, 2, 3. Okay, but why? That's okay. So I'll get back to this third question later on. Okay, let's see. So now, okay. So if you have 5-class classification problem and you want to avoid masking using polynomial regression, what is the minimum degree of polynomial that you use? Is okay 5-class. So using polynomial regression, you are avoid masking for polynomial. Okay, it is B 4. Okay, so number of class -1. Now fifth, consider a logistic regression model where the predicted probabilities for a given data point is 0.4. Okay. If the actual label for this data point is 1, what is the contribution of the data point to the log likelihood error? So the log likelihood error is y log of y, okay, minus y log of y. So you just do because the point is 1, so 1 log of y cap would be there. Okay, so the likelihood equation, let me just write it down. Please note, and it is 0.4, right? So it will be marker minus log of, so y log of y cap, that is the likelihood, right. So now it will be minus 1 log of 0.4. So it will be log of 0.4 is how much, and that is e based. Yeah, minus 3.9. So Okay, it's like it's 10 base, so log of e base we have to do. Ln. Yeah, minus 0.96. This one, okay? Now, what additional assumption does LDA make about the covariance matrix? Okay, this is take fact. See, covariance matrix same for all classes. Okay, so these are factual things. You can just see the theory for this. Yeah, so the descent boundary for LDA is linear because it's a linear method. It doesn't apply any non-linearity. Two classes C1, C2 within class variance. This. Fisher criteria. So I didn't remember this Fisher criteria. Just look it up once, okay? So the answer is for Fisher criteria is B. So 1.26. So let's see. Let's just do this. So two classes C1 and C2 within class variance sigma omega 1 equal to 1 and sigma omega 2 equal to 4. Let's say that what is the project if the projected means are mu1 equal to 1 and mu2 equal to 2, what is the Fisher criteria? So there will be an equation for Fisher criteria. Okay. So what they showed is, yeah, it's something like the class overlap or something. Equation. Yeah, it's mu1, mu2 minus mu1 into 2 sigma 1 plus sigma 2 2. Okay. So just apply this formula, you will get that value, which will become around, it will come around 0.8. Okay. Oh, the solution is also given here. Given two classes, C1 and C2 with mean this and this, especially, what is the direction vector omega for LDA? So it will be just this minus of them, mu1 minus mu2. Okay. Okay, so there will be a constant factor with it also. So just see which one just correlates with the minus, because this property holds. So mu1 minus mu2 would be 3 by 4, right? So 3 by 4 like this. This one would be correlating with it. 0.6, 0.8. Okay, so week 4. Yeah, week 4, most of them are factual, except some. So week 4, one question was there, right? But we are trying to solve. So the first one, this one, perceptron, this was solved in the last class. Now in week 4, this question is also correct. So you just apply all the possible combinations for the SPM and you will get around 0.98. Okay. So and I guess people also get 0.98. Right? Just apply all the combinations that you are supposed to give here. Okay. Yeah. And you'll get it. So for week 4, other questions are from SVM, which are kind of factual, thus represent and all this.
So for seventh question, can you tell how to do, sir?
Which one?
Seventh question.
Seventh, right? Let me see. Yeah, seventh question, I guess it was okay. Let me just show you that part. Yeah. So what you do, uh, you have this iris X and iris Y given, right? So for X, you take 100 examples, and for okay, let me just fix this. One minute. Okay. Now we are okay. So what you do, you have this ID6 and IDSY data, right, given to you in a drive folder. So for the training part, you took 100 examples for training for both of the training X and Y, right? And for testing, you take the rest of them. So there will be 50 data points for the rest. And what you
Just
do, you
basically, we need to download the iris file that they gave and do this
yeah,
program, sir.
yeah. Just download the IDS file they have given. And what you do, you use the perceptron model from scikit-learn. Okay, so not the linear regression or logistic regression model, it should be the perceptron model, and you just apply to L1 and L2 penalty for, let's say, model 1 and model 2. And then after you do, let's say, all the, let's say, you fit the model and then predict, compute the performances, you will see that the maximum accuracy that you can get for testing is 0.78 and 0.664. So those two options will be the correct one. And for SVM, it will be same. So SVM, you have to like apply, I guess, two different kernels, RBF and linear. Let me see. What is the question? Yeah,
So,
for
how to identify the maximum performance, sir?
maximum performance would be, see, for the first one, it is clear, right? You have to, the answer would be 0.78 and 0.64, right? So the seventh
Yes, sir.
question, it is clear. So you have to just train two different models, this with penalty L1 and penalty L2, and then get the testing performances. So the testing performance for the model 1, see the model 1 testing performance is 0.78 with L1 norm, and for model 2 with L2 norm, its accuracy is 0.64. So the accuracies matches for the option D, right? D, and yeah, for the eighth question, which is kind of similar, right? It's same, the modified iris dataset you have to download, and you have to use the sklearn uh, library for the SVM, and take only the first three features, not the two features. So earlier it was, I guess, top two features, right? Only first two features. So here you take top two features. Sorry, top three features or first three features, and then you apply different kernels. So for example, so we encourage you to explore the impact of varying different hyperparameters for the model. Specifically, try different kernels and associated hyperparameters as a part of your assignment training models for the set of the following hyperparameters. So RBF kernel, gamma equal to 0.5, one versus race classifier, and no feature normalization. All those things you do and get and see how much. So these are the kind of
Sir, if possible, can you
defined
do the eighth question,
hyperparameters.
sir?
So these are the defined hyperparameters for the model. So it is defined here, right? So kernel is same OVF and gamma. And no feature normalization means you don't normalize the features. That's it. Okay.
Sir,
So
if
there is
possible,
no,
can you do the eighth question, sir?
can you repeat?
Can you try the eighth question, sir?
Eighth question. Okay. Let me try. So the model definition should be like this. So you can just copy it.
Sir, and also to select the top two features means what in this
Top,
case, sir? For
top
seventh.
three. It's top three, right? Let me just try to do it.
So in here, we for the sound question, we chose the top two options
Yeah,
for sir features.
for
So how
the
did you choose the top two, sir?
top two means the top, not top two, first two. It's not top two, it's first two, right? So it will be like this SVM, sorry, SVM, SVC. So this is your model, okay? Now you have to change the, sorry, so as a part assignment with the following set of five parameters. This is their fixed model. Try C of these values of the for the set of above hyperparameters. Report the best classification accuracy. So the value, so the hyperparameter that will be changing will be only C. Okay. So SVC, this is my model. It's so this is my okay. So this will be double quote. So this will be also double quote. Yeah. Any other step? It is imported. So decision function shape OVM. Yeah, decision function shape will be underscore. So OVR is, I guess, default. Okay, by default it is OVR. Okay, now this is my model. Now how will process the data? I will process the data like this. So I have downloaded these files already. And for top three features, I just take top three indices for the features, right? So 0 to 3. That's the primary change from the seventh question. Now everything is same. So PD is not defined. Let me input pandas. Yeah. Now model.fit, and then you predict on the testing, predict on the not the training, on the testing. So I predict test X test. Okay. Now what will be our evaluation? It will be let me get that function from top processing classification matrices. Just use it here. Okay. Now for this, he is 0.1, right? And let's see what is our score. So our white test, white bread test. Yeah. So our accuracy is 0.98. Right? Let's see for the others what happens. So we have to vary till. So what we can do, we can just copy this model code from here. Right now for C in, how many C's are there? 0.01, 1 and 10, right? So we 0.01, 1 and 10. C equal to C, right? And now you have to take the maximum uh, this, right? Maximum. So it's prediction ready. So I can just take accuracy from here, accuracy, and that's the current accuracy. You put max accuracy, or what we can do just to accuracy, you can take it as an array. Okay. So
Sir, but
accuracy.
didn't we read from the data to get the top three features?
This one, right? You take top three features by this 0 to 3. So I love what it does. So let's see what X train look like. Okay, this is kind of an 2D array with 3 columns and 100 rows, right? But the data set looks like this actually. It's actually 4 columns. Now, what I love does, I take first 100 values as mentioned in the question, right? First 100 values, and then, so if I just do this, there are 100 values. Now, for the column slicing, I have to do this. Take from 0 till before 3. So 0, 1, 2, 3 columns. Okay, now after I run this, see 0, 1, 2, only 3 columns are there. Now values make it a 2D matrix. That's it. So that's how I am selecting top, sorry, first 3 features. Okay. Now what I am doing, I am appending all accuracy computation from the models to an accuracy array. Now if I run it, okay, where is the 0? Okay, here. Run it. All the accuracies are added. So accuracy, if I see, it's 0.32, 0.98, 0.98. Now I have to report the maximum accuracy, right? So just take max 0.98. Okay. So the answer would be A, 0.98. Got it, right?
Yes, sir.
Okay. So let me maximize this. Right. Yeah, you can unmute and speak. No need to raise hand. Okay, so okay, so week 4, week 3 assignment. Any other doubts?
Sir, if these types of questions wherein codes are need to be done, how to do them in the exam, sir?
So in exam, if you are asked these type of questions, then there will be the coding window for this. Okay. So these questions will only come in the coding section of the exam. Okay, it will not come as a MCQ. You have to, let's say, write the code and then uh, give your results as an output, kind of like this. Okay, so it will not come as an MCQ because you have
So
access to your laptop.
will internet connection be available for that? This
No,
all
no.
comments, whether we should be familiar like that.
Uh, so you will not be asked something which is very, let's say, not used or not or very rare, right? So you have to remember these paths. So it- where is the yeah, you have to remember these type of paths at least that yeah, like where the confusion matrix function is located, or where, let's say, SVM, how I can import SVM, right? So I think you will not have any like autocomplete feature in the code, like code ID. Okay, so you have to remember the paths at least. So these things, remembering how to read data frames, how to slice them, these are pretty basic, right? But you can always have the error trace of that ID, and based on that debug your code. Let's say if I have placed something, let's say this kind of error, right? Then it will get a syntax error. Now I can see, okay, now here I get a syntax error, so it should be I log. So syntax error will be there, but you will
How many
not get any.
programming? How many programming questions will?
That I have to check with the professor. So it varies from run to run. Okay. So there is no fixed pattern. Like most of the professors don't follow a fixed pattern. So I will see. But like it will be surely that you will have an ID there to run your code. Okay. But there will be no autocomplete feature. So you have to remember.
Sure. For
Yeah.
the every week assignments that are given, some have coding in them, like the one you did now, but they are
Mhm.
MCQs, no, sir. So why
Yeah.
won't we get MCQs like them in the exam?
No, see, anyway, you have to, let's say, answer in a checkbox fashion. Okay, so you have to maybe just like the assignments, you have to also click on the right option, but there will be a coding ID besides it. If there is a question that is similar to this, okay, similar to yes, yeah, similar to this type of assign. If there are any questions similar to this, there will be a coding ID given to you. No, no problem, because it's mostly implementation type thing, right? You cannot like get this answer in your head. Okay, so you have to run it. So there will be an ID available to you if this type of question comes. Okay, and don't over. So I think some of you are very confused about this question, right? So don't overthink these questions. Just see, okay, these are the basic hyperparameters I have, and this is the parameter I should change. Write a loop, append everything to, let's say, your append
Sir,
everything to your a list of
for which combination did we get that 0.98 accuracy? Because I was
it's
not able to get that much accurate.
yeah, so it's
Only
it's
0.88, I think.
not that much over complicated, right? Just print the accuracy array you'll get. As you see, now you'll get for 0.01 it is 0.32. Now for 1 it is 0.98, and for 10 it is 0.98. So for both 1 and 10 you will get 0.98. Okay, and just see whenever, let's say, you are not able to get that thing right, so just cross check with this code where you are doing wrong.
Sure. So
Yeah,
for the final exam, seeing codes similar to the assignments that we have done is enough, sir.
yeah, yeah. Similar to the, so if you do the assignments rigorously, it will be more than enough to like there will be similar questions in the exam as well. Okay.
So the coding part that we are doing for assignments is enough to learn for the exam,
Yeah,
sir, for
so
coding.
so so it will be enough if you just do this runs assignment as well as the previous runs assignment. So I am
And
currently
how
we
many
are
marks
currently
should we get
practicing
for
this.
our assignments? How many
So
marks for the assignments?
can you repeat? I didn't get your
How
question.
many marks should we be getting for assignments?
Oh, so that distribution is already available here, right? See, yeah. So assignment average score. So 25% of best 8 assignments from the total will be given for the 25%. So best 8 will be taken. From 12 assignments, you'll take best 8. That 25% marks will be there for your like inter final score. And for the exam, you will have 75% weightage. Okay. So these things are already in the course page. If you see, these things are already mentioned. So how much you should score to get a certificate, or yeah, these kind, or how. So how we will calculate the final score? What is the passing criteria? These are all mentioned in this page, this course page. Let me share it with you in the chat.
So basically, the types of questions will be coming similar to the assignment ones we
Similar to
have
the
did.
assignments, exactly. Exactly. So there will be a lot of factual questions for, let's say, so similar question that you see in the assignment, right? So if for LDA, how the reason model looks, it's linear, right? So these type of factual questions will be there. So try to remember the facts as much as possible, as well as there will be these numerical questions, or well, let's say counting is there, right? So you have to count how many number of times a particular class appears, and based on that try to compute something which is by hand. No, let's say programming is needed there, but there can be questions for, let's say, implement these type of SVM or decision tree later on, right? Okay, so yeah, so these type of questions will be there, and just try to cross check your code. So both of the linear, the seventh question and the eighth question code is available here. Okay, so and I will share this with you. So try to cross check your code with this, so you will know where you are doing the mistake. Okay, let's see if I am if I am not doing this right, I'm not slicing it properly for the top three features. Only if I'm missing this, let's see how much my accuracy would change. Right, let's see, you are not slicing top three features. Okay, Now my accuracy would, now similar, so here also my accuracy is 0.98. Okay. So, so even if you don't choose the top three features, then also you'll get 0.98. So there is something you are doing wrong. Let's say if I choose only top two, right? If I just stay with the previous question selection, then see what happened. In that case, you see, you get 0.32 for 0.1 and the maximum accuracy is 0.88. So maybe some of you are doing this mistake that you are only taking top two features, not three.
Oh, that maybe that was the issue.
Yeah, yeah. So you have to take top three features like this. Not top three, sorry, first three. Yeah.
No, that's why yes. When I took top two, I was getting only 0.88.
0.88, right?
Yeah,
Yeah. So that's the
but
issue.
the answer is 0.98.
Yeah. So 0.98 is that we are getting if I'm taking, let's say, first three features, right? So that is correct. And you are supposed to take top three features. See, here they mentioned. Uh, so yeah, use only first three features.
Okay, okay.
Okay. So so
Sir, what is the random state value in the perceptron function, sir?
so for random state, is it mentioned here? Uh,
Yeah, in the question number 7,
Question number 7, right?
in
So
perceptron model function.
yeah, so
Model
is
model.
random state mentioned? It's not mentioned, right? So don't set it. So if it is
Okay.
not mentioned, do not set it. Let's see what we have done earlier.
Actually, sir, in my program, I have mentioned it, and whenever I am changing the random state value,
It will change,
the
right?
result will change.
Change. Yeah, exactly.
Yeah.
So where you have mentioned it? Is it in the perceptron function or
In the
in
in the
the
per, in the perceptron functions or your
perceptron
panel.
function? Right?
Yeah.
Here.
Yeah.
So so you see the by default the perceptron function takes random seed as 42 or something, right? Random state 0.
Yeah.
So,
0.
so you are supposed to compute with 0. So that results will be there. So let's see if I change it random state to 42, right? Let's see what like what is the current accuracy now. Uh, Similarly, for the train test fleet, it took random state as 42. Okay, so just change random state from 0 to 42. See my model performance would change actually. These are training accuracies. Now for testing, we have, yeah, it's 0.46 and 0.56, right? Now, if it is not given, so the question doesn't say anything about random state, right? So just don't use any random state. Use the default random state.
Okay, sir.
Okay.
Okay. Thank you.
So in that case, what will happen? Yeah, now see my accuracy is 0.78 and 0.64, which is from option 3, I guess. It is option D, right? And that is the correct answer, option D. Okay, so whatever information is not given, take it as default.
Okay, sir.
Okay. So this week's assignments are over. Let's see this week's content now. If you have any doubts with me, so I guess you have like for the 5th week you have gone over the videos, right? So you have watched the videos or you're still watching them? For the recorded videos of NPTEL, I'm saying. So yeah. So maybe you are only like watching them this week, right? So we'll touch upon the most important topic of this week, which is how neural networks work. Okay, and we'll try to implement a digit classification model, so handwritten digit classification model, and let's see how much accuracy we can get. And we'll see how the data is recorded and everything. Okay, so it will be clear how, let's say, data sets are organized in real world. Yes. Now, just for a recap, we did this last week. So perceptron, it's only single neuron. and it works like this, that there is a weight for the dendron and there is a cell energy bias. They gets multiplied and added with the input, and they produce the output, right? So yeah, and our objective was to minimize the target. So uh, target is my y, right, actual y, and I'm trying to reach that y with my predicted y cap. So my target is to reduce the error function to 0, so that my y cap becomes y. That's our objective, right? And to do that, what we learned in the previous class, there is a method class method called gradient descent. So instead of, so to follow the gradient direction in a backward order. So if you just take steps backward to the gradient, and gradient is basically the, let's say, where the error function is rising, that direction. If you just take steps backward from that direction, you will reach the minima, right? And that's the objective. That's how you like reduce the error. Okay, so you formalize the error as this function y minus y cap, and then take steps backward to the gradient direction, and just take steps, let's say, with respect to w and with respect to bu, and we implemented it. So if you are confused about this, how these things are implemented in Python, you can just see and watch week's 4 video. Okay, so yeah, and now so the cost function is mean square error. The entire computation looks like this. So update will be omega equal to omega minus learning rate times 2y minus y cap into x, and for b the update equation would look like b minus learning rate times 2 into y minus y cap. Yeah, and this was our simulated data we want to fit, and this is how you implement it in Python. Okay, and this is how the model learns it. So yeah, so this line is, and we'll see how model learned it. Let's see. And these are some kind of how to evaluate classification as well as regression models, right? And let's just see how a particular perceptron learns. That would help you. Yeah, let's. So yeah, so this is my simulated data. Okay. Now, yeah, this is something, let's say, if I randomly try to guess the weights and biases, right? I land here. So we'll initialize the model with 0.1 and 1 as weight and bias. So my model starts as this red line. Okay, it somehow has to tune the weight and bias so that it can represent this scatter plot in a, like, linearly represent this scatter plot, right? Or regress it basically. Now everything is implemented here. We start with uh, oh, so this is how, let's say, an update equation look, right? So if I just change weight to be 1 and bias to be 2, then my model, uh, it is not, okay, so here. So then my model is here, right? So earlier, if I start with 0.1 and 1, it is here. For 1 and 2, it is here. So I have to update the model parameters such a way that it represents my data perfectly, right? So let's start with 0.1 and 1. And we'll see how, and this is the entire training loop. Okay, so this is learning rate. We fixed it to be 0.01, that constant we are multiplying with the gradient, and this is the update equation for the entire data. Okay, yeah, now we start with 0.1 and 1, and see, this is how my model learns. Did you see that? Or I should, let me reduce the learning rate a bit, then you can see it. Oh, sorry, I have to reinitialize it too. Yeah, see, this is how it is learning, and the weights are updated. Okay, so I have to run it for 1000 epochs, let's say. Yeah. So these are the weight changes you are having with epochs. Can you see? It will actually, it is reducing the error function. Okay, we can also plot the error function side by side. Let me plot the error function. And now it is representing my data. And this is for only one neuron or perceptron. Now we'll see how to do the same thing with a neural network, okay? For a digit classification data. So this is a much simpler data set, right? Where we have only X and Y. For the neural network example, we will have X to be an image or multiple values or a vector, let's say, and the output will be which class? Is it 1? Is it 2? Is it 3? Something like this. Okay. So yeah, so you get how perceptron works, right? Now let's see how a page. Now let's see how neural networks would work. Here's my pen. Okay. So for one neuron, the connection looks like this. So there is this perceptron body. You have a axon which takes input X. There is a cell energy bias B, and they gets added and multiplied. Right? And then you have some function. For linear perceptron, it is linear. For general perceptron, it is considered as a step function. Okay, and then you have an output or prediction y cap. Now, what is a neural network? Neural network is when you have multiple inputs. So there can be multiple inputs for perceptron also. Okay, so x1, x2, x3, right? x3, and the change will be omega 1. There will be an omega 1 here, omega 2 here, omega 3 here, and the equation that will be here. The
Sir, can you
equation,
explain this diagram once more, sir?
which one?
The one you do now, sir.
Okay. So there can be, so it's a perceptron diagram, right? So you have a cell which have some energy, initial energy B, and there are multiple inputs. X1, also let's say X1 is here. X1, X1, X2, and there is another input called X3, and all the dendrons have some weight W1, W2, and W3. So the updated equation would look like X1 omega 1, or you can say, we can represent it in a summation, I equal to 1, 2, 3, xi omega I plus b, right? This will be the kind of output here that is represented as z, and then you have a activation function sigma, which can be a, let's say, a step function. Step function are like this. So for some value of z, let's say up beyond 0.1, you have a 1 peak. So 1, otherwise you have a 0. This is a kind of a example of a step function. Okay. So this is how a perceptron looks like. Now let's see how a neural network is different from this. So for neural network, we have multiple stacks of perceptron, and the stacks are kind of subsequently aligned. Okay, so you have one neuron, two neuron, three neuron, and let's say inputs. So these are, let's say, input neurons. Okay, or we can say not input neurons. We can have an input layer actually. So input layer is, let's say, x1, x2, x3. So these are inputs, and we represent them as dots. So those are not real neurons. We just represent them as dots. Now neurons are represented as these type of circles. Okay, so let's say there are let's say there are two neurons for the first layer. It will be easy to understand. Two neurons for the first layer, 1, 2, and then there is another neuron, only one neuron for the last layer. Okay, so this is the neural network. Okay, so why it is a neural network? So if I just draw the connections, it will be clear. So what is the connection for them? So X1 would connect to this neuron 1. Let's say this is neuron, and how the nomenclature is done is like this. No, neuron 1, layer 1. Okay, and this is neuron 2, layer 2. Sorry, layer 1, layer 1. And this is known as neuron 1, layer 2. Okay, now everybody is connected to everybody. So how they're connected? X1 is connected to neuron 1, X1 is connected to neuron 2 as well. Now for X2, just use a different color. It is connected to neuron 1, it is also connected to neuron 2. For X3, let's use black. It is connected to neuron 1 and it is also connected to neuron 2. Okay, now this is where, let's say this is so there will be weights associated to these connections, right? And there are also biases for the neurons. So for this one, let's say bias 1, and this was is bias 2, right? We have two bias components. Sometimes it is represented, sometimes it is represented like this also. So it has a bias 1 of layer 1, or just bias 1, not layer 1, let's say, and it has a bias 2. Okay, now what will be the weights here? So weight 1 1, so it is connecting first input to first neuron. Similarly, this will be weight 1 2. Here weight 2 1, weight 2 2. So it is hard to write here. Let me 2 2. Okay, now here it will be weight 3 1 and weight 3 2. Okay, now let's just see how uh, this is represented at a matrix operation. Okay, so earlier you see for a perceptron it is easy. It is omega 1, omega 2 plus omega. So sorry, x1 omega 1, x2 omega 2, x3 omega 3 plus b, right? For this one to compute, and what we are computing? We are computing uh, activation 1 of first layer. So it is, so these are the nomenclatures. Okay, so activation 1 of the first layer, activation 2 of the first layer. Okay, and there is a, let's say, a activation function also, sigma, in the neurons. Now how they are computed? We can see that activation 1 of first layer is what? Is actually, see the multiplication, x1 omega 1 1 plus x2 omega 2 1 plus x3 omega 3 1 plus v1, and then you have the activation, right? Sigma. So this is the entire, you see, this is the entire computation for activation 1. Now similarly for activation 2, similar, right? x1 omega 2 1 plus, sorry, 1 2 1 2 plus x2 omega 2 2 plus x3 omega 3 2 plus b2, right? So yeah, so these are the two activations for a1 and a2. Now similarly, these are connected, this one and this one, and there are weights associated to this also. So let's say omega 1 1, omega 2 1, only one neuron, so it's omega 1 1 and omega 2 1. So what is the activation for a1 2, or basically this is known as the y prediction, right? Y cap, because there is no further layer. So this is the y. So a activation of the second layer is the prediction. So in that case, my y cap would look like this. So a1 1 omega 1 1 plus A21 omega 21 plus, let's say it has a bias B1. So to differentiate between the biases, we can have a superscript 1, 1, and this is the second layer bias. So here it will be 1, 1. Same for the weights also, you can have superscripts that denotes the layer, okay? Plus B1, 2. Now, because the weights are also similar, we can have similar superscripts. So 1, 1, 1, everything. So you can understand, right? So there will be all ones in the superscript. For this one, 1, 1, 1. And for this one, the superscripts will be 2. And then after you have this, you apply the activation function sigma, you get the output. So this is the entire computation for a two-layer neural network, where the first layer, and these are known as, so from input to output, how many neurons layers will be? Let's say there can be multiple neural layers. So for this case, we are seeing only one hidden layer. So these are known as hidden layer. Hidden, okay, because it is sandwiched between the inputs and the outputs, two kind of endpoints of the network. Okay, let's say there can be 3 or 4 hidden layers also, then our superscript would change accordingly. So for the first hidden layer it will be 1, for the second hidden layer it will be 2. Okay, let's say the last layer or the final layer is the fifth one, right? So the fifth layer superscript will be 5, like this. So this is the entire computation of a neural network. Okay, and there can be, so you can see how it will scale if there are multiple neurons of the first layer, right? It can, so there will be more weights. So if there is another neuron, there will be more connections, the equation will go long. Right? Now we can represent this as a matrix multiplication. So we'll see. So the dimension of this input, let's say it is f, right? F, why F? Because F is the kind of short term for feature. So it is feature dimension. And let's say the next neuron layer has n neurons to be outputted. Okay, so the next neuron layer has n neurons. So what will be the weight matrix? So how we can represent this entire computation of A1 and A2 as a matrix operation? That is the main point. So for perceptron, the matrix operation are like this. X1, X2, X3. So this is the row vector, and you multiply it with omega 1, omega 2, omega 3, right? And then add a single matrix B1 or B, right? Not B1, B. You see, if you multiply it, omega 1 x1, omega 2 x2, omega 3 x3 plus b, you get the same equation, right? So this is how a perceptron model is represented. So the entire x matrix is known as x. Now weight matrix, you can let's say formulate it with a column vector, or if you just formulate it with a row vector, you can write omega transpose plus the b matrix, right? So this is the matrix operation for perceptron. Now the similar approach we can do for neural networks as well. And for just to clarify, if there is a, let's say, activation function sigma here, right? Now you apply the sigma over all entries of the matrices. Yeah. So the matrix operation would look like this. For neural network, from the equation only you can understand. So if I just try to decompose this equation to a matrix, right, it will look like this. So there are 3, x1, x2, x3, right? Now omega 1, omega 2, omega 3, how we can represent it? You see, just follow the multiplication. The out and b1, b2, we can just represent it like b1, b2 for the first layer. Okay, and what will be the output? Output will be, and there is the activation function, obviously sigma, and the output will be a11, a21, right? So we have to fill in the matrix here. So what will be so a1 is how much? X1 omega 1 1, right? So omega 1 1, and what is So how the multiplication is done? 1, 2, 3, and then you'll get 1, 2, 3. So this dimension is how much? 1 times feature, right? Now, and this one is how much? 1 times, so not 1, n times 1, and this is also n times 1. Now, n times 1, we have to do it n times 1, right? So the order should be different actually. Uh, n times 1, this is 1 time f. So if I just do f times n, it will be n 1 times n, right? So you have to take this here actually. F time n, or we can, let me write the matrix first. Just use the indices, okay? Omega 1 1, omega 1 2, omega 2 1, omega 2 2, omega 3 1, omega 3 2. Okay. Now what is the dimension? It's f time f cross n, right? Yeah, f cross n. So you have so after you multiply these two, you have 1 cross n. Okay. So accordingly, you can just do this. So you can formulate the bias to be a row vector. And this one to be a row vector as well. Yeah. So how you will formulate it? This is 1 times n. So we'll formulate it as a row vector. So b1 1, b2 1, and the output will be same a1 1, a2 1. Okay. So see, if I just multiply these two and add the bias, right? You will see that we can compute A1 and A2 very easily. And these operations can be directly done with GPUs. Okay. So you just pass two matrices, it will compute the multiplication addition in a very quick time. Okay. So that's why GPUs are used for training large neural networks, because we can multiply very quickly. Like matrix multiplication can be done very quickly on GPUs. Okay. Because see, so B1 computation is not dependent on B2. So no, sorry, not B1. The A1 computation is not dependent on A2, because see this matrix multiplication, how does it happen? So it gets multiplied with this column, and then again it gets multiplied with this column, right? And they are not kind of dependent on each other, right? So if there are multiple neurons, there can be multiple, let's say there can be multiple other columns as well, right? So in that case, I can do parallel multiplication of these things and get A1 and A2, right? I can, so A1 computation is independent of A2. That's why GPUs, so their architecture is you can launch multiple parallel threads together, which does the exact same operation but on different set of data points. Okay, so you pass this part and this part on one core, you pass this part and this part on another core. They can be done simultaneously. Okay, and you'll get and the bias can be also added simultaneously, right? And then you'll get A1 A2 at the same time if you have enough number of cores, right? So mostly GPUs have a lot of cores. So so earlier I had one GPU that has 1024 CUDA cores. So they can launch a limited number of threads, obviously, but most of the time we can do parallel matrix multiplication on GPUs. Okay. So it takes instead of O of n square time, or let's say not O of n square, if you do matrix multiplication, it will be O of n cube, right? So O of instead of O of n cube time, you can do it in O of n square. Basically, easy n, you can do it in O of n. Okay, if you do for parallel multiplication. So yeah. Okay. So this is how a neural network layer works. Similarly, you can see the same computation happened for layer 2 as well, right? So layer 2, it will be, if I just write the same equation, it will look like sigma activation 1 1 activation 2 1 times, here the matrix would look like activation 1 1 activation 2 1 2 1, right? 2, yeah, 2 1 plus a single matrix B1, which will give you activation 2 1, which is exactly y cap. Right? Now how now let's say I have multiple examples, not x1, x2, x3. I can have x11, x21, x33, right? Then in that case, I can have another, let's say x1 dash, x2 dash, x3 dash to be stacked here. If I just do this, you can parallelly compute for multiple examples also. So that's called batching. Okay, so you can batch examples instead of only one data point. You can send multiple data points in a batch and get the activations for all of them. So let's say another batch I appended to this matrix. Okay, in that case, their activations will be computed here. A 1 1 dash, a 2 1 dash. Similarly for n, let's see if there are n examples batched, and we'll do batching. We'll see, we'll do batching. If there are n examples batched, my output activations will look like this: n1 1 n, a 2 1 n. Okay. So let's see how the shapes are changing. So shapes are important. So my x can be my column dimension is f, my feature dimension, right? And my example can be one or many. So let's generalize it to capital N. So capital N is my batch size and my feature dimension is f. It gets multiplied with f times n, right? F times n. So my output will be n times n, small, capital N times small n. And now how bias, let's say bias is only 2, right? So how the biases are added, it gets cascaded. So it gets cascaded to all the points. So it gets added to, let's say, whatever gets computed, if I multiply this, it gets added to that one. Next one, it's also get added. So it's called cascaded, okay? It's not matrix addition, it's actually cascade. So how you can visualize it? Let's say this is a matrix, right? And you have a row vector which needs to be cascaded. So there are multiple rows in the matrix, right? So it gets added to all the rows one by one. That's it. That is called cascading. Okay. So bias get cascaded to all the outputs. So it produces a n cross n. So the next layer, same batch size. So for all the example, you get next activations. Get it? So this is the entire neural network layer, how it works. So you can represent a network like this. Let's say there is an input node X. What happened? There is a weight matrix W, right? It gets multiplied with the X input. Then it gets added to a bias vector B. This is end of, and then you have an activation, obviously. Activation sigma. So this is representing a one layer. Now that gets passed to the next layer. So, and we'll give the name. So here weights and biases are there, right? After you multiply them, it becomes Z. Multiply and add them, it becomes Z or intermediate. This is, so before the activation, it is known as Z. Okay. After the activation, you name it as A activation. And then this activation acts as a input to the next layer. So same structure would repeat. Okay. The same structure would repeat how? Let's add a multiplication node again. Add a omega. So these are omega 1, omega 2, omega 1, omega 2. This is bias 1. Okay. Similarly, addition would be here. Bias 2 would be here. Bias 2 would be here. Again, an activation function will be there. And this is, let's say, Z1. activation 1, Z2, activation 2, and this structure can repeat as many times as possible. So this is for layer 2. Okay. Now, if there are multiple layers, let's say if there are n layers, this substructure would repeat n times. After that, this let's say n times it repeated, and then you get activation n, right? And that's the output layer, right? That's the output. You repeat it n times. That is known as the prediction or Y gap. Okay. So what you will see in the example, let's not get too much detail on this now, because we have limited time, right? So let's go through back propagations quickly. So you already know the gradient descent algorithm, right? So for a cost function J, if I want to, let's say, minimize it, right? What I will do with respect to a parameter omega, obviously. So yeah, so let's say I have a cost function J and I have a parameter omega. I want to minimize it with respect to omega. So what I will do, I will not go into details how it works. You can see the week fourth video for this. What is the update? Omega equal to omega minus learning rate times, learning rate is a constant. So this is a constant. Constant times times the gradient of J with respect to omega. So that's partial derivative. So this is sigma J divided by sigma omega. Okay, so this is the update equation for learning rate, for gradient descent, or known as gradient descent. Writing is bad. See, gradient descent. Okay. Now I can do the same thing just using the back propagation rule. So the chain rule of the derivative computation, right? I can use that same logic and back propagate the gradient updates to all the previous layers. So I can easily compute gradient for omega 1 and omega 2, right? But there is this path. This path I can follow to compute for B1 and omega 1 also. And let's see how we can compute it. We just uh, take that entire thing. Oh, the lasso selector. Um, Let me do this. Copy, paste. Yeah. Okay, so now let's see. So we have the cost function J here, right? And J is what? J is nothing but MSE, for example, mean square error. Okay. Or that can be anything. So let's say that log likelihood estimate you can also do. So minus y log of y. If it's so MSE is used, for example, in a regression task, right? And log likelihood estimate can be used for, let's say, a classification task. Okay, and we will use this log likelihood estimate for MNIST or handwritten digit classification. You'll see. Now, what I can do, I can compute uh, this delta J by delta A2, right? It is directly computable because A2 and J is directly related. That is J. J is actually y minus, for MSC, it is y minus A2 square. It's y minus A2 square, right? So I can directly compute delta J by delta A2. Let's color it differently. I can compute delta J by delta A2. I get from A2 and Z2 is related related, so I can compute delta A2 by delta Z2. Now Z2 and so Z2 and B2 is related, so I can compute delta Z2 by delta B2. Similarly, omega 2 and Z2 is related. So Z2 is what? Z2 is actually omega 2 A1 plus B2, right? Now, because see the graph, you can see the how this is coming, right? Now I can compute from delta delta Z2 divided by delta omega 2. Now go backward. Now I have A2, right? So A2 is nothing but, see, it's also so Z2 is also related on A1, right? So Z2, there is the input for A1 also. So I can compute delta Z2 divided by delta Z1, delta ZA1. And what will be the output for this? Only omega 2, right? So if I just compute delta Z2 by delta 1, it will be omega 2. Because there is no A1 component with this will be 0 and it will be 1, right? So only omega 1, omega 2. Similarly, here, see, same thing we can just follow. Delta Z1 by delta B1. And here we can do delta A1 by delta Z1. Delta Z1 by delta omega 1. That's the entire computation of partial gradients we can do for the immediate thing, right? So this Z1 is what? Z1 is nothing but omega 1 x plus B1, right? Now let's see from this information how I can. So what are the gradients that we can do that we can compute for updating B1 omega 1? So these are the parameters, right? B1 omega 1. This is the first parameter for the, or this is the second layer parameters. And this is for the first layer parameters. These are B1 and omega 1, right? Now what I can do, I can see, so to update it, what are our goals? So just follow the previous equation, right? This is my update equation, omega equal to omega minus learning rate into the gradient of the cost function with respect to that parameter, right? So if I'm updating omega 2, I'm computing gradient with respect to omega 2 only. Okay. Now, what are our update equation? Omega 1 is equal to omega 1 minus learning rate times delta J by delta omega 1. Similarly, for others too, for V1, it will be B1 minus learning rate times delta J by delta B1. Similarly, for omega 2 and B2 also. Now, what are our objectives from this entire equation? So our objective is to find delta J by delta omega 1 to update omega 1, delta J by delta B1 to update B1. Similarly, for the second layer, delta J by delta omega 2, delta J by delta B2, right? These are our objectives. If I can compute this thing, I can update my neural network and optimize the error J, right? Now, see, these things are not anywhere in the entire thing that we can compute, right? Now here we use chain rule of the gradient computation, a chain rule of the derivative basically. So chain rule, if you remember, if let's say Z is equal to let's so what is the log x square? What is the derivative of log x square with respect to x? It is log x derivative 1 by x square, and then you multiplied the x's derivative as well, the 2x. Now you get 2 by x. So what you did here, so the chain rule looks like this. So dy dx of a function of g of x, right? So here you get f dot g of x times g dot x, right? So this is the chain rule of gradient of, let's say, derivative, right? Now, similarly, see, if I can just multiply out these gradients, the gradients I can compute directly, right? I can just multiply them out and see the gradient of delta j by delta b2. Let's see. So our objective is delta j by delta b2. We can multiply the gradients in this order: delta j by delta a2 times delta a2 times delta z2 times delta z2 times divided by delta b2. Now see, these all will be crossed, and only the remaining will be delta j by delta b2. So I can compute delta j by delta b2 by just multiplying multiplying the gradients in this path, right? Similarly, I can compute, just see, just I can, if I just replace another path, delta j by delta omega 2 is equal to delta j by delta a2 into delta a2 by delta z2. I have also delta z by delta omega 2, right? Everything will be crossed. I get the gradient for delta j by delta omega 2 if I follow, sorry, if I follow this path. Right? Similarly, if I follow this path, I can compute delta j by delta b1. See, the entire multiplication would be same if I just follow this path. So it will be delta j by delta a2 times delta a2 by delta z2 times delta z2 by delta a1 times delta z a1 by delta z1 delta za1 delta z1 by delta b1. Okay, now similarly, if I follow this path, same path, I'm going to the same path, and I just take this path, I can also compute delta j by delta omega 1, right? And after I compute all of them, I just update in a loop this, and let's say omega 2 is equal to omega 2 minus learning rate times delta j by delta omega 2, just omega 2 b2 is equal to b2 minus learning rate times delta j by delta b2. If I just in a loop, if I just update these three, then I can train my neural network model. That's the entire backpropagation algorithm. Okay. Now, if I have multiple mode layers, let's say not 2 layers, let's say 5 layers, the entire computation would be same. You have to just follow the path, follow this path to kind of backpropagate the gradient from one layer to the another one. Okay. You get the entire algorithm, right? How backpropagation is done. Like, if you have any confusions, just clear it now. We will try to implement the digit classifier now. Okay, you guys don't have any doubt, right? Just think on the algorithm first and see which part you are not understanding. You can ask. So what we are basically doing, we are taking the gradient to the previous layer by just following the middle path, this path. And if I want to compute the parameter gradient, I have to just go to the side branches from any layer, right? So if I am, let's say another layer was there, I would just follow to backpropagate the gradient further. I can just follow this path. Or if I want to compute the gradient of that particular layer, I can just follow the branches. Okay. So this is how the entire neural network, this type of neural networks get updated. Okay. Yeah, see you can see the entire picture anyway. Yeah, okay. So we'll continue for one use case, that is a digit classifier. So okay, so what is a digit classifier first? So for example, if I write 2, right? So how the data is represented, first clarify that one. So if I write 2, right? So then my model should predict, if I just give this input, my model should predict I write 2. Okay, this is my task. This is my prediction task. Now, how the data is represented? So it is so MNIST data is represented as 28 cross 28. That means how much? 28 cross 28 is how much? Just tell it. 28 times 28. It is 784, right? So okay, it is okay. Uh, so 28 cross 28 is 784. So it is one particular digit is represented as 784 values. And how the values are represented, you can see, you can just draw a 28 cross 28 grid. Okay? So each pixel represented is one point in the grid. Okay, so I can just write. It's actually 28 cross 28 matrix. That's it. So I'm trying my best to write to draw a grid. Let's say this is a 28 cross 28 grid. Okay. Now how my image is, so how my data is written. So people are asked to write a number in a 28 cross 28 grid. For example, and let's say I write 2. 2 is represented as this. Let's say so this means these points have high values. Okay, I'm just filling them out. Yeah, so this is how 2 is written. Example 2, let's say. So you just fill out all the you get the point, right? So this is how 2 is represented. So this is actually x or input. Okay, and my and these values are also labeled as 2. So there is an associated label. That's okay. This matrix represents 2, or this image represents 2. Okay, now that is a data set. So you have x and y pairs. For this, x is this image, and they have a data set. And what we are trying to do, because we are using simple neural networks, we'll flat it out. We flat it out as a vector. Okay, so how will process? I will, let's say, get the data. We'll flat them out. Okay, so it will be represented as vector, and the vector size will be 848. 784. So the first row will be first. So row first order. Okay. The second row will be next. Oh, sorry. Second row will be here. Similarly, 28 rows will be, so this is the first row, this is the second row, the last row will be the 28th row. So this is how the data is represented. Okay, and there is the associated label y to be true. Now what we will do, we will try to build a network like this. So there are input layer. Input layer is how much? 784 input vector, right? Now this will be given to a layer of let's say 64 neurons, right? Try to compute the number of parameters. We will check how many parameters are there in my Python code also. So 64 neurons, and then let's say there is another 64 neurons. So this is layer 1, this is layer 2, and lastly you have another there are 10 possible digits, right? 0 to 9, right? So my data set Y is actually in a set, is a set from 0 to 9. These are the possible values of Y we have, right? So there can be 10 possible values. So the last neuron layer will have only 10 neurons to classify. Okay. Okay. So how many parameters we have? See, for one layer, what was the mathematics? So omega has the shape of f cross n, and bias has a shape of 1 cross n, right? So for each layer, it will be adding. So omega 1 would have shape of f means 784 cross 64. Bias would be 64. Now here 64 to 64, so omega would have shape of 64 cross 64. Let's change it, right? Let's make it 32. We'll have a better standing. Let's make it 32. So it will be, so here the feature is this one, right? So 64 cross 32, and bias would have 32 parameters, 1 cross 32 actually. Now for this last layer, omega would be 32 cross 10, and bias would be how much? 1 cross 10. See, actually the previous layer is acting as feature, the next layer is acting as n. So here for the second layer, this is f and this is n. For the third layer, this is f and this is n. Okay, so these are the total number of parameters we have. Let's see how many number of parameters we have. Let's add it up. Calculator. So 784 times 64 plus 64. This is the first layer have 50240 parameters plus second layer 64 times 32, and this can come. So you can expect this type of questions. A neural network architecture is given, you are supposed to take how many number of parameters are there for the entire network. Okay, trainable parameters. So everything we can train here, right? Omega 1 b1, omega 2 b2, omega 3 b3, we have to train. So these are trainable parameters. 64 times 32 plus 32. So the second layer is 2080 plus the third layer 32 times 10 plus 10. Sorry, 10 plus, so 3330. So the total number of parameters are 2080 plus 50240. 52650. Okay, see what is the time. Okay, so these are the total number of parameters. We'll try to implement the network first, and then we'll see our data. Okay, we'll come to this number a bit later. So after we implement the network. Okay? Kernel, sorry, kernel restart. Okay. So first implement the network. We will use TensorFlow. Okay. And this is a kind of library that is widely used for implementing neural networks. Okay, and it's very easy to implement a neural network with TensorFlow. You just import it, ef dot, sorry, ef dot keras. You can use the keras tf dot sequence here. Dot sequential. So it's a sequential network, right? So you are basically the first layer output is feed to the next layer. So it's a sequential network. Okay. And then you have to pass an array and a name of your network. Let's say my name. Okay. And this returns you a model variable, model to train, just like your sklearn or something like this, just like your sklearn. Let me zoom this in. Okay. Now the layers, right? Layers are implemented like this: tf dot keras dot layer dot dense. So dense is the layer that we learned today. So there can be multiple other layers too. So there can be specialized layer for image, okay, that are known as convolutional layers. There can be specialized layer for time series. So let's say you have time series data. Now you want to process that. There can be recurrent neural network layers too. Okay, so the basic layer is dense that we learned today. So there can be these stacks of perceptrons that is known as the dense layer. And why dense? Because the connections are dense, right? It is connecting everybody to everybody, right? So that's why it's known as a dense layer. What are the parameters? You see, and what is the network we are trying to implement actually? We're trying to implement this network, right? So first layer is 64, 32, and 10. So the first layer has number of neurons. The input dimension is 784. That is the input vector size, right? Now the first layer has number of neurons, and see, these are the parameters you have. Okay, initialization, everything we'll discuss in the next week, for example. So we have only these two as the important parameters to set. Okay, other things are by default. So none means it's a linear layer. So by default, all dense layers are linear layers. Okay. Now units, I have 64 units at the first layer. So this is my first layer. Let me layer 1. Okay. And my activation can be one good activation for these type of tasks are ReLU activation. And I guess you know how ReLU looks like. It's for all values till 0, it is 0. And then from 0 to onwards, it's X. So it looks like this type of a function 0 and then it's X. Okay. So ReLU is a good choice for this type of neural networks. Let's say I copy the layer 2 and only change the number of neurons to be 32. And now I'm going to the last layer, right? Now last layer activation would be changed. See, last layer I have classification task, and there are multiple things that can be classified. So it's not like a binary classification task, right? So in that cases, my number of neurons will be 10. 10 classes are possible, and my activation will be softmax. Softmax. What it does, uh, maybe I have told you in one of my classes or somewhere how like how softmax is computed. But let me just. So these two layers we have ReLU. Okay. Last layer we have softmax. Why softmax? Let's say I have 10 values, right? E1, not E1. Let's say Z1, Z0. Let's say Z0, Z1 till Z9. Okay. These are the last layer output without activation. So Z. Okay. Now what I do, I have a softmax block. It converts to the probability function. So probability of 0 given the X, probability of 1 given X, probability of 9 given X. How does it do that? So the activation function softmax of Z looks like this: e to the power Zi summation of e to the power Zi for all values of I belongs to 0 to 9. Okay, so what does it mean? It makes these uncorrelated Z values to a joint probability distribution, JDP, joint probability distribution, sorry, JPD. Okay, so now my entire Z values are kind of squashed into the probability distribution of like this. So what is the probability of the value X being 0? So what is the probability that I have passed 0 in the matrix of input matrix, right? Now what is the probability of 1? What is the probability of 2? Till what is the probability of 9? And after you do that, you have a kind of distribution, right? Distribution as output. Let's say my input was 1. Okay, so the matrix input was 1. Okay, this is what I inputted. So my target is to maximize this probability 1 to, so maximum is 1, right? So every other thing would become 0. Okay, so my target is to make this probability function to be 1, others to be 0. So that's why it's a joint probability distribution. You see, if I just sum everything up, the top thing becomes summation of this, and the bottom thing is already summation of the all exponential values, right? So it will cross and becomes 1. So if I just sum all the probabilities, pi given x, right, it will become 1 based on the activation function. So it's a joint probability distribution. So if I am just trying to increase one probability value, it will decrease all the other probability values. Okay, and for this type of activation, my cost function is categorical cross entropy. Okay, categorical, or the log likelihood. So you can also remember the log likelihood. Okay, so for binary it is called log likelihood. Okay, or for multi-class it is called cross entropy, and it's a category wise multi-class, so it's categorical. So there can be 10 categories, right? So it's called categorical cross entropy. For binary class you can also call it log likelihood, or also it is called as binary cross entropy. Okay, now because I have my network implemented, right? Let's cross check our parameters. So this is my network. We run it. Now model.summary, we can print. So what is the problem? Has not built yet, right? So to build the model, what I have to do, I have to just pass one random, just say whatever input size I have, right? So np.random, let me import numpy also. np, or what we can do, we can also build the model by calling it the build function. Model dot see the output. By first calling the build function, you pass the input data you are trying to send. Okay, so my input data is this n cross 786, 784. So model.build. See, now it takes an input shape, right? So my input shape is, see, this is how you represent an input vector shape. Say one single variable tuple. Okay, so just run it. What does it say? Okay, so you have to pass it none comma this. Yeah, none comma this. So none means I don't know the batch dimension now, but I can tell you the feature dimension is 784. Okay, for some, for some these frameworks, this like TensorFlow, it is represented as a single variable tuple. Okay, for TensorFlow it is none comma 784. Now I don't have to pass the predict function now. Now if I call summary, see, so the dense layer first. So my network name is my NN. Okay, my first layer has 5024 parameters. Let's check it with our computation. 50240. The second has 2080 parameters. 2080. The last one has 330. Yeah, 330. And total we have two 52650. So our entire computation was correct, and in memory it took 205.66 KB. Okay, So this is the amount of memory it is taking. Now there can be non-trainable parameters as well. Okay, so you can, let's say, freeze a particular layer, then those parameters will not be trained. So what you are doing basically, you are cutting off these gradient computations. So that these branch gradient computations, you are just saying, okay, don't compute these gradients. I don't need gradient for omega 2. Okay, I will not update omega 2. So in that case, those parameters will be excluded. For example, if I freeze layer 2, right? This dense one means layer 2. So its index is 0, 1, and 2. If I just freeze this, 2048 compute take parameters will come under non-trainable parameters, and that will be executed from the trainable parameters. Right? Here you see, because all the layers are trainable, the total parameters and the trainable parameters are same, but I can intentionally freeze a layer that would reduce my number of trainable parameters, and that gets added to non-trainable parameters. Okay. And how to freeze a layer? It's very easy. So model dot layers. If I just, let's say, take the first layer, right? So the second layer actually dot trainable equal to false. So this is how, if I just now run the summary, you see, now my trainable parameters are reduced and the non-trainable parameters are added. So the second layer is added to the non-trainable parameter list. So those computations will not be happening. Okay. Anyway, so we need all the layers to be trainable for now. Now let's just get the data now. So the data we can get it. So if you have any questions, unmute yourself, ask. Okay. Digits. Yeah. So this is my data, and see, this is how my data is organized. So my data has a huge array. The targets are given. Frame is none, and these are the pixel values. Target names, right? Target names. Target names are 0, 1, 2, 9. Right. So there are always, and images. Images means how much? Images. Yes, there are some images. Oh, images means it's without, it's the 28 cross 28 things. So data is actually flattened out. So we'll see. If my data, I can see saved. It's actually flattened out. This many example with 64. Why 64? Let's see how the images are look. Oh, okay. So for this case, for this data, we have 8 cross 8 images. Let's download the digits data. Okay. MNIST data set. Tensorflow. Let's say Tensorflow, they have a MNIST data set. Okay. Yeah, load MNIST, this function. So we'll not use this data set. Instead, we will use this data set. MNIST. MNIST is equal to this. Now it's downloading the entire data. Take some time. Okay, downloaded. MNIST. So it has 4. See, if I just do length, it's a tuple. Length. It's a 2 length tuple. Okay. Now MNIST 0 has again 2 things. So one is this entire thing and the array of the targets. MNIST 1 also have a big array and then the targets, right? So it's training and testing set basically. So let's see what is the shape first. MNIST 0, and then we'll take X for the 0 and then shape. Yeah, 600 images, 28 cross 28. Okay. Now my X train is this. So if I just take one, it is 600 labels, and how they look like this. So 50 like this. Okay. Okay. Now how I can I'll break everything up. Let's say MNIST X train. y train x test y test. This is how the entire thing is stored, right? Yeah. Let's see again. MNIST. So one array. Okay, the values. Then the second array, and then the values. Okay, fine. So this is how you extract entire data. Okay, X train. I can now see it's if I just take the shape, it's a 60,000 images with 28 plus 28. Let's see what is the first image look like. Import at plot dot pyplot as plt. plt.imso is function, a function that is there for plotting images. Okay, so if I just take out the first example, extrain 0, it's like this, and the associated title y train, sorry, y train 0. So the associated title is 5. So if I just, let's say, if I just go and plot for I in range 10, if I just plot 10 such examples, to get an overall idea, right? So x is equal to plt dot subplots. Okay, now we need in rows, number of rows equal to, sorry, number of columns is equal to, let's say 10. So we have x is I, is I, and this is set title. Uh, so what they're saying, trigger of, okay. So this is axis. Yeah. So this is how my examples look like. So this is 5, this is 0, this is 4, 1, 9, 2, 4. Okay. Got the data, like how the data is organized, right? Now, currently my data is like this, but my neural network takes data as a shape of 784 vectors, 784 value vectors, right? So what I have to do, so this is pre-processing. What I have to do in terms of pre-processing, the first step is reshape my x to be a 60,000, 784 matrix, and again I have to, let's say, scale it, right? Let's say min max scaling I can use, min max scaling. Okay, and we already know that these are pixel values, right? So my minimum value is 0, maximum value is 255. Okay, so these are the two pre-processing steps we will do. So x train is equal to x train dot reshape, or let's say dot flatten, or you can reshape. Reshape, and reshape what it is, -1 mean I don't want to know the dimension. Okay, so the entire 60,000 dimension remain as intact, or let's just explicitly mention the dimension 60,784. Just reshape it to this dimension. So all 84 cross 84 will be kind of stacked as a long vector, the row major order vector. Okay, and what we can do to scale it, the scaling function, we can just create a scaling function, scale x. Now return x minus minimum divided by maximum minus minimum. This is the min max scalar, and because we know that it's a image data, we already know that the minimum is 0 and the maximum is 255, and we can use that same scale function here to scale it. Same thing, you can apply it to X test. Only I have to change this dimension. So let's see what is the shape of X test. Thousand, right? 10,000. Yeah. So this is the X test. Okay. Now we have scaled it as well as we have shaped it. So let's check it first. Train, shape. Oh. So it's shaped properly. And if I want to see the maximum value for this, it's 1. The minimum value should be 0. So now my data is scaled as well as shaped properly. Now, because we are using a framework like TensorFlow, it is very easy to train my model now. What should I do? Model.fit, same as the sklearn library. Model.fit, and we have to pass few parameters. So x, y, see the parameters. X, y, epochs, how many epochs we should rotate around the entire data. Verbose, let's keep it auto. Split, everything. These are like, we'll discuss it later on for the validation and everything. But for now, let's only tune these two. Okay, shuffle should be also true. Shuffle. So I pass the entire data. It will bash the data, like set at capital N dimension. Okay, it will not send 60,000 data at once because it will be very heavy computation, right? The multiplication will take longer amount of time. So it will send, let's say I can send only 32 images at a time. So it will batch and send the data, compute the gradients, update the parameters for that 32 images. And it will repeat until it exhausts the entire data. That is called an epoch. So let's train my data. Let's train my model. Train. And you can implement this on from scratch also, from the algorithm we have learned today. Okay, let's take my batch size to be 32 and let's go for 100 epochs. Okay, and returns a history history parameter. Okay, we'll see what history returns. Now if I run this, oh okay, one thing I forgot, I have to tell the model, right? I have to tell the model that okay, I am training for this loss and I want this optimizer. So usually the optimizer, that gradient descent thing, has different names like SGD, Atom, and like RMS prop. These are different type of optimizers that run on the same principle, that compute gradients, update the parameters. Okay, for you. So before training, I have to let the model know that okay, I am training for this model.compile. This is how you tell the model that okay, I'm training for this loss and use this optimizer for training the model. Okay, and what is the, yeah, and you can also set up matrices. So what should be reported after each training loop. Okay, so we'll use these three things. Now I am training for sparse categorical cross entropy. Oh, sorry. My optimizer is Atom. My loss is sparse categorical cross entropy, and my matrices are accuracy. Okay, so HSURASTY accuracy. Now this is how I tell my model. Okay, use the Atom optimizer that use the gradient to update the parameters. Use sparse categorical cross entropy as the loss function, and report me accuracy after each batch and after each. Okay, so after each update, it will tell what was the accuracy on that batch. It will tell after each epoch, entire loop, it will take what was the average accuracy per batch, right? That was the this line. Okay, so if I run this now, see, it is the average accuracy 90, 96, 98 based on the data. Now it is training for 100 epochs. See, after each batch, it is computing the average accuracy at the end actually. So each batch, the accuracy thing is changing actually for each batch. At the end, it is getting computed as the average accuracy and reported here. So it's already reached 99.6% accuracy. Okay, 33, 34, 37. Let's just wait a bit so that it gets completed. So meanwhile, if you have any doubts, do you have any doubts? Okay, so we'll wait till the model is completely trained. 80, right? And what it is basically doing, it is computing the gradients per parameter. So for all the this 52650 something parameters, right? How many parameters were there? Yeah, 52650 parameters, updating all the parameters, and then then computing the accuracy based on that. Okay. Yeah, now my model is trained for 100 epochs when my training accuracy, average training accuracy per batch is 99.8%. Okay. Now, what does this history gives you? History. Yeah, it gives you loss per epoch. And because you have mentioned accuracy to be one of the metrics I want, then it also give you accuracy. You can see them actually. PLT dot plot and it's a dictionary, so you can just access it with the keys. So this is the loss function. Okay. And just ACCURAC accuracy. And this is the accuracy you get with respect to epochs. Okay, so for 100 epochs, you get 100 accuracy values. Now let's evaluate our model on the training data as well as the trace data. So train data. And we can actually use the same function that we have implemented earlier, right? Here, the compute classification accuracy matrix. Training data, add that function here. For training data, we have to predict first. So ypred is equal to model dot predict. Now predict will give you, let me show you first, x train. It predicted for all the data points. Ypred, it gives you probability values actually. Okay, so what is the probability of the first example? So there are 60,000 examples in the training class. So what is the probability of the first example to be 0, to be 1? So if I just, let's say, take the sum across axis is equal to 1, it's all 1, right? So if you just take the sum of the all probability values per example, it is 1. Okay, and there are 60,000 such joint probability distributions that get predicted. Okay, now to predict the class, right? So there sometimes there is this predict class function, or what you have to do, take the argument max. So you take the maximum argument. So you take the argument which has the maximum probability value, okay, for each class. So that is known as argmax. Argmax of the ypred. So take the argument which is the maximum probability mass associated with on axis is equal to 1. So for all examples. Now you get the predicted, you see 504. Now you get the predicted classes. Okay. So this is known as ypred and this is known as ypred. Okay. Now I have probably predicted classes. Now I can use this easily. My first parameter is y, so y train, comma y pred. Now this is my entire compute. So this is main matrix. Okay, my result on train set. Result on train. Now if I want to print the classic confusion matrix, then I can just go ahead and print the confusion matrix out of it. You see, this is my confusion matrix. So my 0th class is predicted to be 0 most of the time, and there are some confusions obviously. So how this is uh, PLT dot heat map. Oh, sorry. PLT doesn't have heat map. We have to import C1. Yeah. Okay. And this is how my data gets classified. So all my data gets classified correctly, except some that are very minute. So if I just, so by printing them, we can observe, but by scaling them, we cannot, by scaling them in a color. Yeah. So these are things 5 to 12. There are very minor things that get misclassified. And if you just go and see those images, they're actually where, let's say, the image is so distorted or it's so ambiguous that it looks like a 9, but it's a 4. Okay. That these things can happen. So this is for training data, right? We can also do it for testing data. Yes, testing data. Okay, let's yeah, just test. Dolce. Okay. Now this is test prediction. Oh, sorry. This has to be test and again test file and the confusion matrix. Yes. Oh, it's still similar, right? It's also yeah, it's also classifying it properly. Let's see what was the, let's print the class confusion matrix. Yeah, there are some mistakes, but it's okay. Now, what was the classification report? So for the testing one, the classification report gives us a kind of overall understanding of how it's performing on each data, right? And what is the overall accuracy? See, it is, you can see it here. See, it's classifying most of the images correctly, and the average accuracy you are getting is 0.98. Okay, now let's see how the model is predicting for some top, let's say top 10 or top 20 examples. We just copy the code up here. Okay, so this is x10 now, x test I, and I have to reshape it again, reshape it to 28 cross 28, right? Uh, and the title should be ypred I. See, these are my predictions. So this is 7, this is 2, this is 1, this is 0, this is 4, 1, 4, 9, 5, 9. Now let's go for more examples. We'll see. So let's print 100. So in rows to be 10 and these to be 10, right? So there are 100 examples I have to print. Okay. Okay. So 10, let's go with a double loop. J. We have ij here. Ij. And now how I can classify this? 10 times I plus j. 10 times I plus j. Okay. Oh, what was the error? Indented block. One indentation should be there. Yeah. So this is my entire so what we can do, we can put the axis PLT dot xticks to be 0, set xticks to be 0, set y ticks to be 0. So there are no these kind of numbers. So y ticks to be 1. Okay. Let's use plt.xticks. Okay, xticks is not there. Maybe xticks is there. Oh. Yeah. Now see, this is the titles are titles are kind of getting overlapped. Okay. Guilty dot tight layout. It gives me, so the images become too small, right? So I have to increase the figure size. Size to be 10,10, let's say. Yeah, now you can see. And identify one misclassification if you can find. And these are all predictions that the model is giving you, right? So 772, these are all fine. I think they're all fine, right? So let's identify one where there is a misclassification. Okay, so I can test this is equal to y print. I have predicted data true, right? I want to see where there is false. So NP where um, or I can just do this. True. I can just press do not of this. Oh, no, it doesn't work. So I just reverse it with 1 minus. Okay, so now when there is a false match, there is 1. Okay, so I can just do np dot argmax of this entire thing. So when there is a 1, we will get an 18. So 18 has a misclassification. So 18, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 18 has a misclassification. Yeah, see this one, this is 18. It's a 3, but it's 8. I can check it. 3. Let's print this one as well as the predicted one by if by test. Okay. Now if I do this, yeah, see, it's predicted 8, but it's actually a 3. So this one is a misclassification. And you can see why the misclassification happened, right? It's very similar to an 8. Okay. Yeah, similarly, if I can find another one. No. So within the first 100 examples, only one example is there, which is misclassified. Okay. So yeah, so this is how the let's say you have to you can implement a neural network to let's say classify digits. Okay. I'll share the code base with you. You can just play around with it. Any questions till now, or any clarifications you want on the code or the theory? You can ask now. So we'll close the call after 3 minutes. Sorry. Okay, no question, right? Fine. So I hope you understand the entire session. Okay. Okay, so let's close the session for today. Okay. If you don't have any questions, so or you can anyway, if you have any questions like later on the week also, you can post it in the WhatsApp group. So you can check it there, okay? So I'm stopping the recording. Stop recording. Oh, sorry, let's stop sharing first. Stop recording. Okay.